All right, today we're going to be taking a look at radical expressions and equations. So one of the fundamental functions we learned back in Algebra 2, we're going to be working through those today here as well. We're going to be able to simplify them, add, subtract, multiply, divide, but also be able to solve them whenever you see that equal sign. So that's kind of our goal of this video. To start though, it's just kind of important to note some of the vocab of this. You know, the root is just the either square root, cube root. Sometimes there's a number there if it's like a cube or a fourth, or just a square root doesn't show it. You got the radical symbol, your standard symbol here, and then the radicand is what's on the inside. But how do we simplify these types of expressions? This could be done with variables, but it could also be done with numbers. It doesn't really make a difference. It could be using the same properties either way. But if you had the square root of 2 plus the square root of 3, we can't add those up together. They're not referred to as like terms. You need to have the same radicand, the same inside, in order to add them. So this would not be, it's not equivalent to the square root of 5. That's not a true statement. But this one here, the square root of 2 times or multiplied by the square root of 6, we can multiply those, and we can call that the square root of 12, which we could break down to 4 times 3, so it's 2 square root of 3 in its simplest radical form. In this next one, what is trying to be pointed out is the fact that if we're going to use our multiplication property, the square root of negative 2 times negative 6 is the square root of 12, which would be 2 square root of 3 as well. But if you type this into your calculator, you will not get that same exact answer. The reason we need to identify the square root of negative 2 as the square root of 2i. Same thing with this, square root of 6i. Now we can say the square root of 12, but then we have I times I, which is I squared. So remember, I is the square root of negative 1. It's just a radical. But when you square that, you get negative 1. That's that whole concept of I. It is a number that when you square it, it is still negative. So this is really I squared, or in other words, negative square root of 12, or negative square root of 2, or sorry, negative square root of 3 times 2. So negative 2 square root of 3. So a little bit of difference. But then this time we're thinking about square roots, and we got some things on the inside. These are separated by multiplication. In the same way that in this right here, I broke apart 12 to say 4 times 3, because I know the square root of 4 is 2. Well, in the same way, the square root of a square cancels the square and square root out. They undo each other. So the square root of x squared, I can just call x. The square root of y cubed, well, there's one group of y squared in that, and then there's another y if I were to break apart the cube there. So a y comes out and a y stays in. And then the square root of z, I can't break that apart any further, so that's its simplified form. And no, you don't need this multiplication symbol in between the two. It should just be smushed together. So that's simplifying when there's a product on the inside. So these properties here, all pretty straightforward. It's just based saying if you got the square root of a plus the square root of b, notice they're different. It is not the square root of a plus b. But multiplication, it is equivalent, and you can multiply it. A square root top and bottom, if you guys recall, this is what's referred to as rationalizing a denominator, something that's done many times in the past, especially in pre-calc, quite a bit. So this would just be the square root of b squared, so it's just b on the bottom, and then ab on the top. And then if you have the nth root raised to the n, those cancel and just end up being b. And there's some variations of this with plus or minus or absolute value that we could see as we go, but those are kind of like our standard properties. So let's take a look at just a couple simplifying ones, and we're not going to do all of these, just we're going to touch on some of them and then move on to some of our more advanced ones, and then also the solving. So square roots, just make sure you break apart to ones that are square rootable, so 25 and 3, 5 square root 3, right? The same thing can be done with fourth roots. So think about numbers that aren't square rootable, but fourth rootable, right? Or that could be cube root. You could try to break that apart as well. You know, a fifth root, and you have a fraction. Well, you can take the fifth root of the top and the bottom and break it apart that way. And now you have the fifth root of 3 over 2. That's the fifth root of 32. We did an example like this on the previous slide. We're going to skip this one. But one thing to note, this 16, just simplify that and call it a 4 out in front. Then do the same thing with the x, the y, the z, and the b, and just take out what you can, leave in what stays. On this next one, since it's all separated by addition here, we cannot individually square root them. But what we can do is we could call this x plus 3 squared in factored form, and now those simplify just to be x plus 3. And you'll see on this next slide, it just gets into some distribution or some trying to simplify. I'm not going to run through this whole one on the top here, but if you have two quantities being multiplied together, you still just distribute. Multiply right here, multiply right here. Just use your properties. Same thing here, multiply and multiply. So you can do your standard distribution practice even with something like this. The one on the bottom is the same idea of rationalizing from right here, but there's an addition or subtraction in the bottom. So in order to rationalize this one, we have to use, if you guys remember, it's called conjugates. So when you multiply two irrational conjugates together, they become a rational number where there is no square root anymore. So we would multiply the top and the bottom by its conjugate down here, which is just addition or subtraction. That's the difference between conjugates. Square root of 3 plus the square root of 5. And then we'd have to do a full distribution here. And then we'd have to do a full distribution here. But you use conjugates to rationalize. All right, that's the main idea for this question. And once again, like I said, this video is just introductory, kind of covering the content. You've learned this in the past, just trying to show some examples and get those refreshers as we go. Moving on to this next one, very similar, but dealing with I. You just have to recall when you do the distribution, combine like terms, but anytime you have an I multiplied by I, that is I squared, and we know that is equivalent to -1. So just remember that. This one has to be rationalized as well because we know I is a square root, so that falls under the rationalizing category. So you would use its conjugate, 2 plus 4i, 2 plus 4i, and then you would do a whole lot of distribution and simplify. Okay, so use those conjugates whenever you have to rationalize. And then moving on to solving. So there'll just be a couple solve questions here we'll try to run through. Dealing with square roots. Just like we learned with most other functions, when solving, you try to use inverse operations. So we have currently something that's square rooted. What you can do to keep the balance is you can square both sides. 2x plus 1 equals 16. 2x equals 15. X equals 15 halves. Well, let's take a look at this next one. They look very similar. The only difference, one has a positive, one has a negative. So let's square both sides. Let's see what happens here. Square them. 2x plus 1 equals 16. 2x equals 15, and x equals 15 halves. Okay, we got the same answer. Seems like it should be okay. Wrong. Okay, here's the issue. This problem right here has no solution. All right, think about this problem. We have a square root equal to a negative number. There is no solution for this one. The way in which you know that is by checking. Literally plug it in and see if it makes it true. Take this 15 halves, plug it in right there. 2 times 15 halves plus 1. That is 15 plus 1, which is 16. Square root the 16 and you get 4, but hey, the other side said -4. That's not equal. So we know that it's no solution. So be careful with the square roots when they're set equal to negatives. It's going to be a no solution situation. Cube roots, on the other hand, you can solve those because you can cube root negative numbers just fine. You can cube root negatives or positives, so these could be solved and it would work out fine. So I'm just going to show one of them with a cube root. Move the 7 first. So your goal is to isolate this. So we have cube root 3x minus 4 is equal to, subtract the 7, 2. Cube both sides. 3x minus 4 equals 8. And then you have 3x equals 12. X equals 4. If you were to check it and plug it in, it works. That is our solution. The other side, we could do the same thing, go through the process, and it will work as well, because remember, once again, you can cube root negatives. Here's the thing about a problem like this, though, I want to point out before we move on. 3x minus 4 plus 7 equals 9. What you cannot do is cube, cube, cube. That does not hold true. That is not a true statement or an equivalent statement to what we started with. You can cube both sides. You can square both sides. You cannot cube or square individual pieces or terms, okay? So be careful with that. One proof of it is just this. 2 plus 3 equals 5, right? That's a pretty standard statement, but square each of the numbers. 2 squared is 4. Plus 3 squared is 9. Equals 5 squared, 25. That is not true. By doing that operation, you change the balance, you change the equivalency, and it does not hold true. But what you can do is this. Square both sides. And that is a true statement still, okay? And last problem for the day. This one's complex. There's a lot going on here, okay? We've got two radicals here. It would be great if you could do this, but we just talked about it. Not that easy. Can't do it, okay? So not possible. So what we're going to have to do is think about algebraically how we could solve this. And I'm going to show just the first couple steps, and that'll be it for the video. What we would want to do is isolate one of those radicals. So let's move this x plus 2 to the other side, okay? So I'm going to subtract it. So now we're left with this. 1 minus the square root of x plus 2. So what I would do here is to isolate this, I would square both sides. Notice that now goes away, and it's just 3x plus 7. That makes that side pretty easy to solve now, because it's just a 3x and a 7. The other side, though, here's what you have to be careful of. You need to actually write it out twice and do some distribution. So it becomes 3x plus 7 is equal to, let's distribute, 1 minus one of those minus another one of those, and then plus, when you multiply these two together right here, the square roots cancel and you get x plus 2. So let's see where we're at. Let's try to clean this up a little bit. 3x plus 7 is equal to, well, now there's negative 2 of these, and then we have a 1 here and a 2 there, so it's 3 of those. Let's move the x and move the 3, subtract it. And then from here, once again, our goal is to get rid of these square roots. From here, we could divide by negative 2. Or you could square both sides right now. It's kind of your choice. Right here, we could do this. Square, square. 2x plus 4 times 2x plus 4 is equal to, make sure you square this, 4 times x plus 2. So all you have to do to solve this from here, do a whole bunch of distribution. After you've done the distribution, it's going to be a quadratic, set it equal to 0, solve it from there. But what I'm showing in this portion of the video is that when you have 2 of these here, you cannot just square square. What you have to do is isolate one of them, square both sides. Then there's going to be 1 left over. Isolate it, square both sides. So it's a repeated process, okay? So most complex question of the day. That's it for this video. Let me know if you have any questions.